Okay, are 1, 1, and 2, 2 linear independent vectors? No. How can you tell? One's a multiple of the other. One is a constant multiple of the other. If you have a list of more than 2 vectors, determining linear independence is much harder, and that's what we did a lot in our linear algebra class. But when you just have 2 vectors, determining linear independence is not hard, right? If one is a constant multiple of the other, that's a way to think of it algebraically. Or if you want to think of it graphically, think of these as points, 1, 1, and 2, 2. If those points lie on the same line through the origin, then they are not linearly independent. Okay, true or false? 3x plus 2y is a linear combination of x and y. True, that's the definition of a linear combination. When you take constant multiples of things and add them together, you're creating a linear combination of those things. Okay, so this, I was thinking, I meant it to be not a hard question, but it might take a little bit of, might take a few times of actually writing out what this means before you can translate it in your brain. So we can write what out this means. Yes. Yeah. So this y prime, that's a vector that represents x prime, y prime, right? And then I've got the matrix 1, 2, 3, 4. And this vector y represents x, y. Okay. So this hint part, like you do need to know that, but using the book, following the book's notation, like this is just going to start to be assumed because they use the same notation all the time. All right, so then to translate into what does x prime equal, what does y prime equal, you do the matrix multiplication, right? So we've got x prime, y prime equals, and remember we talked about how to do this last class, you take the first row dot product with the first column. So this is a 2 by 2 matrix, and this vector is a 2 by 1 matrix. So the inner dimensions match, they're both 2's, so I can multiply them. And the outer dimensions are going to be my answer, a 2 by 1. So I've got a 2 by 1 matrix, so I like to just sort of write it down and put blanks for the answers. 2 by 1 matrix. And I dot product 1, 2, and xy, and I get 1x plus 2y. And then I take the dot product of the 3, 4, and the xy. It's the second row times the first column, so it goes in position second row, first column of the answer, 3x plus 4y. So now I've written this as one vector equals another vector, which means their components have to be equal, right? That means x prime is 1x plus 2y, and y prime is 3x plus 4y. After you've done this once or twice or 5 times, you start to be able to look at this and say, oh, that's 1x plus 2y, 3x plus 4y. Yeah. Yep. Okay, so again, to review the notation, remember that a linear system is the form x prime equals ax plus by, and y prime equals cx plus dy, right? So it's just a system of differential equations that's linear in both x and y. The exponents on the x's and the y's are both all ones, and the coefficients are just constants. A, B, C, and D are just constants. Yeah, when they write a bold y, they mean the vector xy. Yeah. Yeah, so our new matrix notation, we have bold y prime equals A times y, right? Which means bold y prime means the vector x prime y prime. The capital letter A means the coefficient matrix A, B, C, D, coefficients from the system. And bold y means the vector xy. Right, so this is key to being able to translate these things. So I've got this linear system, y prime, bold y prime, so that's the vector, y prime, is 2, 3, 0, negative 4 times bold y, which means the vector xy. So if I was going to translate this, before I try to answer any questions, I should probably like wrap my brain around what this is saying. So this says that x prime, y prime, right, that's what bold y prime means, is equal to 2, 3, 0, negative 4 times bold y means xy. So if I was going to translate this to sort of a more natural way of writing a system of equations, like just as two equations, this would be 2x plus 3y and 0x minus 4y. Yep. Yep. It's the derivative of y. Yeah. So capital Y is just a vector xy, right? So capital Y prime is the vector x prime y prime. Which is the slope of a vector. Yeah. Yeah. In the xy plane. I know. I know. Okay, so I want to verify that these two vector valued functions, y1 and y2, right? So y1 and y2 are both bolded because they are vectors, right? And that means they mean x1 of t, y1 of t, right? So instead of writing capital Y bolded, I could write x1, y1. It's a vector. Equals e to the 2t, 0. And capital Y2, that means x2 of t, oops, y2 of t. That equals negative e to the negative 4t and 2e to the negative 4t. All right, so this is going to take a little bit of effort. I've given you two possible solutions to a system of differential equations. So before break, we had spent, in like the 2 or 3 classes before break, in all of those classes, I was asking you to check, are these things solutions, right? So, and it's tedious, right? But it's kind of one of those things that's nice because you can always do it. You can always check, even if it's tedious. All right, so I have two potential solutions, x of t, y of t. Yes. Oh, I totally took it from right there. Yeah, I was just copying. Yeah. And so these are pulled out of the sky right now. I'm just giving you two potential solutions. We're going to check and see if they are actually solutions. Starting on Wednesday, we're going to figure out how to sort of come up with those things on our own. But today, we're just checking. All right, so I'm just going to start with this one. I'm only thinking about this potential solution. So solution 1. I just want to verify that this is actually a solution. Does this x of t and y of t satisfy the system of differential equations? So I've got x prime is 2x plus 3y, and I probably didn't leave enough space here for us to do this. Y prime is negative 4y. Okay, so what is x prime? Looking at solution 1, what is x prime? 2e to the 2t. Yeah, so x is e to the 2t, so x prime is 2e to the 2t. Okay, I'm just replacing x prime with the derivative of the given x. I want to know, does that equal 2 times x? So I'm replacing the x here with e to the 2t, plus 3 times y, and what is y? 0. Okay, is that equation true? Yeah, 2e to the 2t definitely equals 2e to the 2t plus 0. Okay, so we've satisfied one of the equations. Let's check the other equation. All right, y prime equals negative 4y. What is y prime? I'm looking at just solution 1. Yeah. If y is 0, then y prime is 0, right? Does that equal -4 times 0? Yes. Yeah. So this system of equations, if x1 is e to the 2t and y1 is 0, we satisfy the differential equation. Okay, so this is definitely a solution. All right. Everybody okay with that? Okay, I'm just going to do the exact same method again, but this time I'm going to look at this guy, solution 2. So this is a second potential solution to these two functions satisfy my system of differential equations. So I'm going to write down my system here. X prime is 2x plus 3y. Y prime equals -4y. Now looking at solution 2, what is x prime? 4e to the -4t. Right? So it's e to the -4t times -4, chain rule, right? All right, does that equal 2 times x? So I'm going to do 2 times -e to the -4t, just replacing the x with the given function, plus 3 times y, replace the y with 2e to the -4t. Are those two equations, are the right side and the left side equal? Yes, because this is going to give me 6e to the -4t right here, and this is going to give me -2e to the -4t. You combine them, and you get 4e to the -4t. Okay. That's fine. What'd you do? Uh-huh. Okay. I think that's okay. All right, let's look at my y prime equation. Y prime is, what is y prime supposed to be? -4y, right? -4y. Okay, looking at y2 here, what is y prime? -8e to the -4t. Does that equal -4 times, replace the y, 2e to the -4t? Yeah, those are the same. Okay, so we verified, I have given you two solutions to the differential equation. So you have to sort of get used to seeing these written as vectors, right? When I write e to the 2t 0, that means that's a function x of t, the top is x of t and the bottom is a y of t. Okay, so there's not too much new here from last class, except that I'm forcing us to use this new notation. And if as long as it takes, just write out what those things mean, right? As long as it takes for that notation to become ingrained. All right, I would like to evaluate y1 of 0 and y2 of 0. So let's rewrite what's y1 of t. That is e to the 2t 0, right? And y2 of t, it's a vector valued function, and it was -e to the -4t and 2e to the -4t. Yeah, okay. So what I want now is to plug in 0 for t for both of these. y1 of 0 and y2 of 0. Both y1 and y2 are functions of time, so I'm replacing my t's with zeros. y1 of 0 would be e to the 0 and 0, 1, 0. And y2 of t is going to be, yeah, sorry, 0, thank you. -1 and 2. Good. So remember what this means. You don't always have to write this down. As soon as it starts to click that you know what this means. But for now, this, what I just wrote here, this means that x1 of 0 is 1 and y1 of 0 is 0. Right? This is two initial conditions, x of 0 and y of 0, just written as a vector. And this one, this means that x, for my other solution, x of 0 is -1 and y of 0 is 2. Okay, are these two vectors linearly independent, 1, 0 and -1, 2? Yes, one is not a constant multiple of the other. These two things are linearly independent vectors. Okay, so now I'm going to take a linear combination of those two given functions, the things that we verified were solutions. I'm going to take a random linear combination of them. I just picked some random constants, 2 and 3. I'm going to do 2y1 plus 3y2. That thing's called a linear combination of the solutions y1 and y2. And I'm going to call the result y3. Okay, so y3 of t is 2 times, I'm going to replace y1 with, it was e to the 2t 0, I think, plus 3 times y2 is -e to the -4t, and 2e to the -4t. All right, and then when somebody from linear algebra can share with the class, how do you multiply a constant times a vector? Yeah, you just distribute. You just multiply every term in the vector by the constant. So this is going to be 2e to the 2t, 0, plus -3e to the -4t, and 6e to the -4t. And then how do you add two vectors? Yes, yeah, everything in the top row you add together, everything in the bottom row you add together. So you add component-wise. So I end up with, these actually aren't like terms, so I just have to write out that I'm adding them. 2e to the 2t minus 3e to the -4t, and 0 plus 6e to the -4t. So this is x3, y3. That's what they asked me to find. And I switched notations here. They used capital Y3 with the vector. Same thing. Any questions how that works? Throw in the constants, distribute, add component-wise. All right, so I have a new sort of, oh, and I was supposed to verify that this is also a solution to the system, right? And I definitely don't have room to do that. Yeah, that's one of the principles of linearity, that the book says this is going to be a solution, right? You got it. Yeah, I'm just going through the steps of showing that at least it's true this one time, right? Okay, so remember that my system was x prime is 2x plus 3y, and y prime was -4y. That's my system. And I've already shown that my first two things were solutions, and now those were given. Now I took a linear combination of the two things that were solutions, and I will show that it's also a solution. So look at my new x here, 2e to the 2t minus 3e to the negative 4t. What is x prime? What is the derivative of that? 4e to the 2t plus 12e to the negative 4t. Yeah. Okay, so that's x prime, and I want to verify, does that equal 2 times x plus 3 times y? So 2 times x, replace the x with 2e to the 2t minus 3e to the negative 4t plus, oops, minus 3 times y, which is 6e to the negative 4t. And I'll do the y equation underneath. All right, so are these two things equal? Let's see, I'll distribute my 2 here, and I get 4e to the 2t minus 6e to the negative 4t. And then this becomes minus 18e to the negative 4t. And this guy and this guy are like terms. So I have 4e to the 2t. Ooh, what happens? Do I have a negative sign problem? That's supposed to be plus, yeah, plus 3y. So that becomes plus 12e to the negative 4t. And that does equal x prime. Check. All right, then my y prime equation, y prime is supposed to equal negative 4y. So look at y, which is 6e to the negative 4t. What's y prime? Negative 24e to the negative 4t. Does that equal negative 4 times 6e to the negative 4t? Yes. Okay. From the beginning, the original system. Yep. Yeah, so let's sort of look big picture here, what we're doing. Go back to the beginning. I gave you this system of equations, right? Right? X prime is 2x plus 3y, y prime is negative 4y. And then I gave you two solutions. I said, look at these two things, these two functions, y1 and y2. Show that they're solutions. And we said, yep, they're solutions. Okay, good. And then I said, okay, now take a linear combination of the two things that we know are solutions. And we were able to show that that thing, that linear combination, is also a solution. And we did that on another page. Also a solution, the linear combination. This, so I started with the given x prime equals 2x plus 3y, right? So I said, all right, x prime, this is x, right? It's in the x location of the vector, and I took a derivative of that. Yeah. Okay, so my linear combination of two known solutions was also a solution. So that's cool. And then I want to evaluate y3 of 0. So that just means I want to do y3 of 0 means plug a 0 into my vector valued function y3. So it's going to be 2 minus 3 is negative 1, and this is going to be 6. Negative 1, 6. All right, so this is a direction field. Talked about these before break. For the system that we've been working on. I want to sketch in the solutions curves that correspond to y1, y2, and y3. And I know that y1 of 0 was what, 1, 0? 1, 0. And I know y2 of 0, I calculated that was, I don't remember, y2 of 0, we did back here, negative 1, 2. Negative 1, 2. And then y3 of 0, the linear combination of the two solutions, its initial value is negative 1, 6. Okay, so each of these things, each of these vectors is really like a point in the xy plane. So y1 of 0 is 1, 0. It starts right there. And if I try to follow the vector field, it looks like it just stays on the x-axis. So there's that guy. That's y1. And I should put a arrow to remind me that that's a vector. And y2 of 0 is negative 1, 2. And if I try to follow the vector field, it looks like it just heads straight for the origin. That's y2. And y3 is negative. I think it just stops at the origin. It's really hard to tell from a vector field. Y3, we've got negative 1, 6. And this one, if you try to follow the vector field, we see it definitely curves. It definitely does something like this. And that's y3. So if you look at the y1 and the y2, there's special solutions in this system, because if I were to pick any other random initial coordinates, like the solution curves look curvy, right? Something like that. So most initial conditions have curvy solutions, but y1 and y2 were special in that they look like they might be straight lines. And this is not verifiable right now. It will be on Wednesday. But those are special solutions to the phase portrait. They're both straight lines, not typical of solutions to this system, and we'll learn to exploit those special solutions on Wednesday. But for now, I just want you to notice them. There are solutions to the system that are straight lines. Okay, so what we just did was a demonstration of the linearity principle that you read about in your text. Here's what you can take away from the linearity principle. It says, for a system of linear system of differential equations, if you have two solutions, y1 and y2, if you're given two solutions or you found them somehow, and k1 and k2 are any constants, then y, some other y, k1 y1 plus k2 y2, which is called a linear combination of the solutions y1 and y2, is also a solution. And in fact, that linear combination, k1 y2 plus k2, sorry, k1 y1 plus k2 y2, is actually the general solution of the differential equation. When, right, if, only if, y1 of 0 and y2 of 0 happen to be linearly independent vectors. If they're linearly independent, then all you have to do is take a random linear combination, just throw some constants, some unknown constants, k1 and k2, or c and k, or a and b, whatever. Throw some unknown constants on your two known solutions, add them together. You've got the whole general solution, as long as the two vectors are linearly independent. We already talked about what linear independence means, right? And when y1 of 0 and y2 of 0 are linearly independent vectors, we call y1 of t and y2 of t linearly independent solutions. So still a piece of vocabulary. All right, the linearity principle is important because it says that to find the general solution, which is typically hard, finding general solutions, right? To find the general solution of a linear system of ODEs, all you have to do is find two particular solutions that are linearly independent. If you can find them, whether they're given to you or you guess them or we learn some method of finding particular solutions, all you have to do is take a linear combination of your two particular solutions and you've got the whole general solution, every possible solution that exists. So in today's demo, I was giving you the two particular solutions. In the class activities, I'm going to ask you to use lucky guess to come up with two particular solutions. But don't worry, the rest of chapter 3 is going to help us develop some better analytic techniques than than lucky guess or me having to just give you solutions. Today is just all about using linearity to come up with the general solution. So finding those two particular solutions we'll worry about later.